friends, last we discussed about the periodic motion, oscillatory motion and simple harmonic motion. In this chapter we are mainly discussed about the simple harmonic motion and its constant. How we represent the simple harmonic motion, or what are the displacement of a particle performing a simple harmonic motion. What should be its velocity, what should be its acceleration, what is the position of a particle during its simple harmonic motion at any instant of time. We are going to discuss this thing. Because this simple harmonic motion of a particle represents the oscillation about their mean position. For that purpose, today we are going to discuss about the periodic function. Now, again we revise what is the definition of simple harmonic motion. A periodic motion of a particle about a fixed point under the effect of the force towards the mean point and directly proportional to the displacement of a particle. Such motion is known as simple harmonic motion. So in short, the simple harmonic motion of a particle is take place about its mean position, like this way. Already we discussed there is a motion of a pendulum of a wall clock. As you consider there is a pendulum of a wall clock that is suspended by a rigid support, so it oscillates like this. So particle perform the motion between two fixed points. There is minus A, there is the plus A. That is the x is equal to 0. So its value x is equal to plus A in this direction, positive x direction, and x is equal to minus A in negative x direction. So how we represent this motion mathematically? For that purpose the periodic function is required. Now the periodic function in trigonometry represented by the sine and cosine. Because the shape of the sine and cosine is continuously changes with time, already we know that the shape of the sine and cosine function is like this way. Sine is this function and cosine is this function. Sine and cosine. That represents the sine function, that represents the cosine function. So here the displacement is also changes with time. At some instant of time is 0, some instant of time there is a maximum positive value, and some instant of time the displacement of a simple harmonic oscillator is negative. Therefore 0, maximum, again 0, again minimum, this way. And due to that reason, the displacement of a simple harmonic oscillator mathematically represented by the periodic function. For that purpose, today we are going to discuss about the periodic function, the explained periodic function. The displacement can be represented by a mathematical function, and this function depends on the time or the time variable. Again, the displacement can be represented by a mathematical function of time. The periodic functions are used to represent a periodic motion. Actually here, the simple harmonic oscillator performs the periodic motion between the 2 points. At definite interval of time, this motion is repeated, therefore that is known as the periodic motion. Okay. Now, the simple periodic function is Ft is equal to A cos omega t. A cos omega t. What is the omega? Already we discussed that is the angular frequency. Omega is equal to 2 pi f and f is equal to 1 by t. Therefore, omega is equal to, here, omega is equal to 2 pi f is equal to 2 pi upon t. That is the angular frequency. Simple periodic function is Ft is equal to A cos omega t. Omega is the angular frequency. Omega is equal to 2 pi f, but we know that the frequency and periodic time has the relation is reciprocal, therefore f is equal to 1 by t. Therefore omega is equal to 2 pi upon t. Therefore periodic time of this motion t is equal to 2 pi upon omega. So periodic time of this function is t is equal to 2 pi upon omega. Because omega t is increased, by an integral multiple of 2 pi. Integral multiple of 2 pi radians, and the value of the function remains the same. So after the one oscillation, suppose the particle starts its motion here. So first go in this direction, again return back at that. So one oscillation is completed. At that time, the phase of this oscillation is increased by 2 pi radian. Phase of this oscillation is increased by 2 pi radian. After this increase of 2 pi radian, so again the motion is repeated. Motion is repeated between the plus A and minus. And due to that reason, we can represent the simple harmonic motion by the mathematical function, that is the periodic function, by A cos omega t. A cos omega t. Not only we represent by the cosine function, periodic function is the cosine function. Suppose, if we consider a sine function, what's happened? So ft is equal to A sine omega t. Instead of the cos, we consider the sine function. Therefore, it is also a periodic motion or a periodic function with the periodic derivative is t. But what is the difference between the sine and cosine function? In sine function, yes, we consider t is equal to 0. And instead of time t is equal to 0, so omega into t is 0, sine 0 is 0. Therefore, its graph is represented by this. At time t is equal to 0, the particle is also at equilibrium position, that means the mean position. For sine function, the initial time t is equal to 0, the particle is at here. Now about the cos function, what's happened? Yes, we represent the simple harmonic motion by the cos function. Time t is equal to 0, omega into 0, 0, cos 0, 1. At this time the ft is equal to A. Therefore, the initial position of the particle is this. T is equal to 0 for cos function and t is equal to 0, x is equal to 0 for sine function. So only the initial position of the particle will perform the simple harmonic motion is changed by considering the sine or the cosine function. If we consider cosine function, so initially the simple harmonic oscillator is at x is equal to A position. And as we consider the sine function, so at time t is equal to 0, the simple harmonic oscillator is at minimum position. So that is the difference, but we can represent by sine or the cosine as a requirement. Okay. Now, if we consider the linear combination of the sine and cosine function, that is also represent a periodic motion or the simple harmonic motion. Therefore, the function is ft is equal to A sine omega t plus B cos omega t. A and B are the constant. Okay. It is also a periodic function with time period t. Not only the single sine and cosine function represent the periodic motion, but the linear combination of these two trigonometric functions sine and cosine, so that also represent a simple harmonic motion. Ft is equal to A sine omega t plus B cos omega t. Okay? The periodic function with the periodic time. Here the periodic time is also t. Okay. Now, as we consider A and B, if is equal to A is equal to D cos phi and B is equal to D sin phi. D sin phi. Substitute the value of A and B in equation 1. What's happened? Ft is equal to, instead of A, we substitute this value, D cos phi sin omega t. Plus, instead of the B, we substitute the D sin phi cos omega t. In both terms, D is common, therefore sin omega t cos phi plus cos omega t sin phi. Now, remember this in 10th standard, we learn about that sin alpha plus beta. Sin alpha cos beta plus cos alpha sin beta. So here the same thing, sin alpha cos beta plus cos alpha sin beta. Here instead of the alpha omega t, instead of the beta phi, therefore sin omega t cos phi plus cos omega t sin phi. Therefore we can add, instead of this bracket, sin omega t plus phi. Therefore d sin omega t plus phi. So here there is obtained by using this equation sine alpha plus beta is equal to sine alpha cos beta plus cos alpha sine beta. Here we are using this mathematical concept to attain this sine omega t plus phi. D is an resultant amplitude. Here d and phi are the constant. D and phi are the constant. Where the d and phi are constant, d is resultant amplitude and phi is the phase. Initial phase. Initial phase, that means when the simple harmonic oscillator starts its motion. So what is its initial position at time t is equal to 0? That is represented by phi. We discuss more about the initial phase and also amplitude in next question. Okay. So d is an resultant amplitude and phi is the initial phase. And due to that reason, I don't mention here what is the phi. Only we mention the d and phi are the constant of simple harmonic motion. How we find out the value of d and phi? So mathematically from this equation we can find out the value of d and phi are. Now adding and squaring the equation 2 and 3. Equation 2 and 3 are this: a is equal to d cos phi equation 2 and b is equal to d sin phi. First we make the square and then adding a square plus b square is equal to b square cos square phi plus b square sin square phi. B square is taken common, therefore cos square phi plus sin square phi. Already we know that the cos square theta plus sin square theta value is 1. Using this concept, so this bracket has the 1 value. Therefore s square plus b square is equal to d square, and taking the square root on both sides, so d is equal to under root of s square plus b square. Under root of s square plus b square. So d represents the resultant amplitude of simple harmonic motion. Now, taking the ratio of equation 3 is b is equal to b sin phi and 2 is d cos phi. Therefore, b upon a is equal to d sin phi upon d cos phi, d cancel. Therefore, tan phi is equal to b upon a. Therefore, phi is equal to tan inverse b upon a. By knowing the value of b and a, we can find out the initial position of a simple harmonic oscillator which represents the simple harmonic motion. Thus, we can represent the simple harmonic motion mathematically by the periodic function. And periodic function is either the sine function or the cosine function or linear combination of sine and cosine function. Whereas there is only for understanding never asked in exam to clear a concept about the simple harmonic motion and how we represent them mathematically. Simple harmonic motion is the motion of a particle about their mean position under the influence of the force acting towards the mean position and directly proportional to the displacement of the particle from the mean position. So how we represent for that purpose? Mathematically represented by the periodic function. And it is not necessary the simple harmonic motion is represented by the sine or the cosine function. That is depends on what is the initial position. Clear this? Okay. Okay, now last we discuss about how we represent the simple harmonic motion by mathematical equation. So for that purpose we are using the sine and cosine function. So ft is equal to a cos omega t plus phi or a sine omega t plus phi. So according to the sine and cosine function, the different initial position of a simple harmonic oscillator. Generally, we are using the cosine function to represent a simple harmonic motion. Now, the next question to clear a concept about the simple harmonic motion. For that purpose, explain the position of a particle performing simple harmonic motion at different time. One particle is, that is the pendulum of a one clock, it oscillates about the mean position. That is the extreme point, or the end point of this path, this and this. So pendulum is oscillate between these 2 points. So at what time the position of a particle or corresponding to the position of a simple harmonic oscillator, what about its velocity? And how we represent by the mathematical equation, that is our aim for this answer. For that purpose, for simple harmonic motion, the displacement of a particle from mean position varies with time. During the simple harmonic motion, the particle executes a simple harmonic motion about the mean position. So displacement of a simple harmonic oscillator from the mean position varies with time is represented by this equation: xt is equal to a cos omega t plus phi. Again, xt, x is represent the position of a particle at any instant of time t. Is A is the maximum displacement from the mean position on either side of the mean position. Cos omega, omega is the angular frequency of this simple harmonic oscillator between these 2 extreme points. T is the time and phi is the initial position or the initial phase of oscillation. Whether A, omega and phi are constant. Here the different figures are shown. So here the simple harmonic oscillator is oscillate between the plus A and minus A. X is equal to plus A and X is equal to minus A position. O is the mean position of a simple pendulum or the simple oscillator. The figure shows the position of a particle performing simple harmonic motion are at discrete value of time. So these 6 figures are given. So here the position of the particle are shown at different time which perform the simple harmonic motion. Each interval of time is t by 4. What is the capital T? Periodic time. The time taken by the particle to complete the one rotation or the one evolution. Here the particle starts its motion from this, first go to this extreme point and again return back to this point. So here the one oscillation is complete. So here this time t is divided in 4 parts. Therefore, after each and every t by 4 interval of time, we represent the position of a simple harmonic oscillator or the particle. With the phi is equal to 0, the initial phase is 0, and t is the periodic time. Again, the figure shows the position of a particle performing the simple harmonic oscillator are at discrete interval of time, or the discrete value of time. Each interval of time is t by 4, with phi is equal to 0 and periodic time t. Omega is the angular frequency of oscillation. Now, for a given simple harmonic motion, A is amplitude, the velocity and position of a particle at time t is determined by the phase omega t plus phi of cosine function. Now, for simple harmonic motion is represented by this equation: xt is equal to a cos omega t plus phi. Here A is the amplitude. Now, the velocity v and position of a particle is determined by the phase omega t plus phi of cosine function. Clear this? There is a basic concept about that. We are going to discuss about the position of a particle performing the simple harmonic motion in different time. So first figure we consider here at time t is equal to 0. What is the position of a particle from this equation? X is equal to a cos omega t plus phi. So here in equation of simple harmonic motion, xt is equal to a cos omega t plus phi. Initially we consider that the phi is equal to 0. And also we know that omega is equal to 2 pi upon t. 2 pi upon t. First we substitute in this equation, therefore xt is equal to a cos omega is equal to 2 pi upon t into t. So here, so that is our equation 1. Here we substitute the different value of time t. Here we consider the t as each interval of time is t by 4. So first we substitute the t is equal to 0 in this equation. Therefore x at time t is equal to 0. So it's equal to a cos 2 pi upon t into 0. That means the 0. Cos 0 is 1. Therefore xt is equal to plus a and velocity is 0. That means at initial time t is equal to 0, the simple harmonic oscillator or the particle is at plus a position. So this, the particle is at here, plus a position at time t is equal to 0, at initial time t is equal to 0. Just to start its simple harmonic motion, therefore its initial velocity v0 or the v is equal to 0. Clear this? Again, the figure A, how we do this figure? Or what is the position of a particle performing the simple harmonic motion at discrete value of time, and each interval of time is t by 4. For that purpose, we consider the equation of the simple harmonic motion xt is equal to a cos omega t plus phi. Here phi is 0, initial phase of oscillation is 0, and omega is equal to 2 pi upon t. First we substitute these two values in this equation. Therefore xt is equal to a cos omega is equal to 2 pi upon t, and phi is 0, t as it is. Okay, first we substitute the t is equal to 0, initial time t is equal to 0 in equation 1. That is our main equation. We substitute the different value of time in this equation. Therefore xt is equal to a cos 2 pi upon capital T into small t is 0. Therefore this bracket becomes 0. Therefore a cos 0. Cos 0 is 1. Therefore xt is equal to plus a. At time t is equal to 0, that is shown in figure first. Time t is equal to 0, the position of a particle performing the simple harmonic motion is A. That is the initial position where the particle is at end point, therefore its velocity is 0. Because in simple pendulum, so pendulum is oscillate like this way. When it reaches at this point, for one moment remains stationary, because at this point the direction of motion is changed. Initially the direction of motion is this. Now for one moment it remains stationary, and then its direction of motion is changed like this. Again going to this extreme point, for one moment it remains stationary, direction of motion change, so again it moves in this direction. So at extreme point, the velocity of a simple harmonic oscillator is 0. And when the simple harmonic oscillator is passing to the midpoint, at that time its velocity is maximum. This, because the force is acting during the simple harmonic motion is directly proportional to the displacement and towards the mean position. Therefore at mean position velocity is maximum. At extreme point x is equal to plus a and minus a will be 0. Therefore the velocity is 0 and x is equal to a position. Now second, t is equal to t by 4. Because we divided the periodic time t in 4 parts. Therefore t is equal to t by 4. Substitute in equation 1. Therefore xt is equal to a cos 2 pi t into t by 4. This. So what's happened? T cancel here, 2 cancel. Therefore a cos pi by 2. Cos pi by 2 0. That means the particle is at mean position. X is equal to 0 position. So that is second figure. Here the particle is at mean position. Now the particle started motion in this direction. And here the velocity is 0. When it passes to the mean position, its velocity becomes the maximum. And the position is this. At time t is equal to t by 4. Clear this? So that is written here. Now, taking the next time interval is t by 4 plus t by 4, that means the t by 2. For t by 2 time, here we substitute the small t as t by 2. Therefore, xt is equal to a cos 2 pi upon t into t by 2. T cancel, 2 cancel, cos pi. Cos pi is minus 1. Therefore, x is equal to minus a position. Therefore, x is equal to minus a and velocity is 0. Because the particle is at extreme point on left hand side, at time t is equal to t by 2. So here the x is equal to minus a position. Here, therefore, for one moment, the particle performing the simple harmonic motion is remains stationary. Therefore, velocity is 0. After that, the direction of its motion is changed from this point. Now, taking the third t by 4 time, t by 4, t by 4, t by 2, plus t by 4, 3t by 4 times. Substituting this equation, a cos 2 pi upon t into 3t by 4. T cancel, here there is the 3 pi by 2. 3 pi by 2 again 0. Therefore, the particle is again at the mean position. At mean position. When the particle passes to the mean position, its velocity is V maximum, same as this figure. But here, the direction of motion is opposite. In figure 2, the particle is moving in this direction. Now, in figure 4, the particle is moving in opposite direction. That means the left to right. So here, the position is 0 and velocity is maximum. Velocity is maximum. Now, fourth time t by 4 time. So t by 4 plus t by 4 plus t by 4 plus t by 4. So that is the t. So t is equal to t. We substitute in equation 1. Therefore, xt is equal to a cos 2 pi upon t into t. T cancel. Cos 2 pi again 1. So it's equal to t. Therefore, the particle is at its initial position again. Here. So here again the velocity is 0. For one moment, the particle remains stationary and then its direction of motion is changed. So at t is equal to t time, t is the periodic time. The time required to complete the one oscillation is known as the periodic time. Therefore, after the capital T time, the particle completes the one oscillation and return back to its initial position. So there is the xt is equal to plus a and v is equal to 0. So again we take the next t by 4 step on the time interval. What's happened? So t is equal to t plus t by 4, that means the pi t by 4. Substitute in our equation 1. So xt is equal to a cos 2 pi upon t into pi t by 4. Therefore pi by 2. So here the v is maximum and particle is at 0 position here. Now here the second oscillation is started. Now as we consider the particle moving on a circular path, this way. Having the radius is capital A. Radius is capital A. And as we consider the projection of this particle on the axis, so this projection, motion of the projection of the particle performing a circular motion represents the simple harmonic motion. Initially, here the particle at time t is equal to 0 at here, so there is the x is equal to a point. Now, in t by 4 time, the particle performing the circular motion is at this point. So its projection on the x-axis is at written at point 0, this point. Velocity is maximum. Again the t by 4 time, the particle is at this point. There is the end point on other side. There is a time t is equal to t by 2 because there is the t by 4 plus t by 4, that means the half time of period, or the half period time. So particle is at x is equal to minus a position that is shown here. So the projection of this particle also exists at x is equal to minus a. That means the particle performing the circular motion complete the half circle or the half rotation. Now again next t by 4 time. That means the 3t by 4 time the particle is at here. Its projection on x-axis again return back to its mean position. So this position. Here the velocity is maximum. And again the t is equal to t by 4 times. That means the 1, 2, 3, 4 times t by 4. So t is equal to t. The particle return back to its mean position. This. Yeah, again the velocity becomes 0. Therefore the particle moving on the circular path, its motion, its projection is moving on the x-axis is like this way. Thus the simple harmonic motion or the motion of a projection of a particle performing uniform circular motion is also a simple harmonic motion. We discussed later about this question, answer the question. But here the position for different position of a particle performing the simple harmonic motion, we discussed the position and velocity of a particle.